Going to wait to see if it's streaming. I'm going to stay here for 1 hour. And I'm going to study the peer-to-peer network from Ethereum. It looks like they changed the documentation for GIF, which is a very good thing. Because it seems like there's a lot more information than they had before. Last time I saw this. But I don't think I'm gonna look too much into this for now. I'm gonna study the source code with ChatGPT helping me. I think I'm probably gonna do the Italian thing first. Let me already put there. And also I started this again, which is the process of running the node where you have to wait a couple of days until you sync. And this process, as far as I did the last time, it's kind of like you're downloading the blocks or the history. And you have to run GIF on one terminal and then Lighthouse or whatever other, I forgot what's the right name, but the connection or the other connection on the other terminal. So it's kind of like the front end and back end kind of thing, where GIF is the back end connection and Lighthouse is the front end. Well, obviously it's not like that, but it has to do. It is this way now because of the proposer builder, like the separation between the builder and the validator, I think, which I haven't studied too much, so I don't know very much, but as far as I understand, you have to run two different nodes now because they separated the people that make the blocks and the people that validate the blocks. And the reason why they did that is because of the MEV, where if people that validate the transactions are the same ones that build, then you get into a bunch of different problems because of the ordering of the transactions, and it becomes a centralizing force because people are incentivized to manipulate the chain to gain more MEV based on gas wars and things like that. And it gets extremely complicated. And I stopped studying this some time ago. But I studied a lot of this stuff already. And mainly just reading a bunch of articles and trying to build the bots, the arbitrage trading bot. So I had to study a lot, but I still obviously have a lot to learn. And it was pretty easy this time because I already had everything pretty much set up. The only thing that I had to do was to download the GIF client again, which is a lot easier now to do, I think. You just go to the documentation, and then I'm using Windows, so you can just download from Windows and it sets everything up for you. And then you have to put the thing on the path as well, which is not that hard to do. You just go to here, and then environment variables, and then you put on path, and then you put the path there. And then you do the same thing for the Lighthouse, and I run both of them on this folder here. And then, as far as I understand, it starts updating the information here, where you start to download the history, which probably this is the part that I stopped last time because last time I ran this, like I didn't want to shut down the computer because I wasn't sure if it was gonna mess up the whole process. But now I understand that it doesn't. All you have to do is put or press Ctrl C on the terminals, and then it activates a process of terminating the chain, and then you can go back to it. But I think I learned that the previous time, but the previous time I had a problem because I was running the node and then the energy cut out, I think, after I had left for a couple of days. And then I had to resync from the beginning because it corrupted, the moment it was shut down, it corrupted the database. And then I didn't research too much to see if there was a way to start from the place I stopped. Because all the information that I found, like the stuff that I tried to do, it wasn't working to start from where I stopped. And I think it's because the database was corrupt, and then I didn't want to spend too much time researching that because I had a lot of other stuff to do. And this happened, I think, 2 or 3 times, and then by that point, a bunch of other stuff was happening, so I decided to not do it anymore. But now I will see, hopefully I'm able to go Like this time, I'm not leaving the computer on all the time. I'm just leaving it for the day while I'm using, and then I'm gonna press Ctrl C and then stop running, and then go like this until hopefully it's synced all the way through. But then I don't know like if anything happens after that, if it's different or like how it works. I know that you can open another console and then you can communicate with your own node using the IPC, I think, connection endpoint. But this is the stuff that I want to clarify more now, and especially looking at the source code because I think it's gonna allow me to understand more, but it's gonna be very hard to do. So I hope that I can use ChatGPT to figure out which of these folders and files are the most important to see first. And obviously I don't know Go yet, but I think it's not that hard to understand if you know other programming languages. It's pretty much everything is always the same. And then there's slight differences here and there that I'm just gonna look it up. Or I can use ChatGPT to clarify the code. I think first I'm gonna try to figure out what are the files that are the most important. And then after that, I'm gonna go to the files and look at the functions like the way that I'm doing here. And then I'm gonna put the functions on ChatGPT and ask to clarify what's going on. And also I have to search what is the difference between this y, let's go, and this, difference from equal. Like what is the difference between this symbol here and the equal sign that I don't know really well. It's for declaration plus assignment, where it's for assignment only. Okay. So it's just a convenient way to do both things at the same time. And then I guess you can do either one of them separately if you want, and there are probably special keywords for them. Like for assignment, probably you don't use anything, or maybe you do. I don't know. See if there's other variables. But mostly the one that I've seen the most is this equal sign with these two dots here. But I assume that, yeah, you declare by putting the name here. Like it's probably similar to JavaScript, where you do const. Yeah, this is different because it's initializing with this parenthesis here and initializing a bunch of them at the same time. But I guess the pattern is the same. Just a different way to initialize, but it's the same thing. You use var, lat, or const, and then if you don't want to use that, then you just use the two dot plus the equal sign. And that's assigns and declare at the same time. Pretty easy to understand, I think. Yeah. So the hardest part is understanding the design of the thing. Like the overall picture. I'm not really sure how I'm gonna go about doing this. I assume this is probably one of the most important files just because of the name, but so this is probably the one that is responsible for discovering the nodes in the neighbor. Yeah, I want to know how does it do that? And also I should probably download the Lighthouse client as well. Yeah, I remember I did that in the past, but then I deleted it, I think. I had problems with the computer and I had to delete it, I think. And also probably gonna read some stuff about this proposer builder separation or something like that. I think it's proposer builder separation, PBS. And try to understand the MV boost as well. The main thing I'm trying to understand is just what is fundamental about the connection, like what is essential about the way that the nodes connect with each other, and the process of the cryptography involved in the consensus mechanism. Because the flow of the shoe is what determines the essence of the blockchain, I think. Like the reason why is different from everything else. So let me think. I think I'm gonna start with the um, with the Italian thing, and then I'm gonna go back to this. Then I'm gonna read this stuff here probably, and then I start using ChatGPT. Sure. I think I'm not gonna be able to do too much today because it's already late here. And I finished all the articles for algorithms as well. So by tomorrow I'm gonna have more time, I think, to study this stuff and build the articles.
Fa,
I forgot to change this stuff.
Does.
fisso.
Fisso.
Set. Unchanging.
3.
3.
3.
Desiderare.
Desiderare.
Desire.
Aria.
Aria.
Air.
Bene.
Bene.
Well.
Anche.
Anche.
Also.
Giocare.
Giocare.
Play.
Piccolo.
Piccolo.
Small.
Fine.
Fine.
End.
Mettere.
Mettere.
Put.
Casa.
Casa.
Home.
Leggere.
Leggere.
Read.
Mano.
Mano.
Hand.
Portare.
Portare.
Carry.
Grande.
Grande.
Large.
Compitare.
Compitare.
Spell. Words.
Aggiungere.
Aggiungere.
Add.
Anche.
Anche.
Even. Also.
Terra.
Terra.
Land.
Qui.
Qui.
Here.
Devo.
Devo.
I must.
Grande.
Grande.
Big.
Alto.
Alto.
High. Tall.
Tale.
Tale.
Such.
Seguire.
Seguire.
Follow.
Atto.
Atto.
Enact.
Perché.
Perché.
Why.
Chiedere.
Chiedere.
Ask.
Maschi.
Maschi.
Men.
Cambiamento.
Cambiamento.
A change.
È andato.
È andato.
He. She went.
Luce.
Luce.
Light.
Tipo.
Tipo.
Kind. Of thing.
Spento.
Spento.
Turned off.
Bisogno.
Bisogno.
Need.
Casa.
Casa.
House.
Immagine.
Immagine.
Image.
Provare.
Provare.
Try.
Noi.
Noi.
Us.
Di nuovo.
Di nuovo.
Again.
Animale.
Animale.
Animal.
Punto.
Punto.
Point.
Madre.
Madre.
Mother.
Mondo.
Mondo.
World.
Vicino.
Vicino.
Near.
Costruire.
Costruire.
Build.
Se stesso.
Se stesso.
Himself.
Terra.
Terra.
Earth.
Padre.
Padre.
Father.
Yeah, I'm not sure if this is doing much. I think for one of the words, some of the words I'm able to remember, but I think it doesn't matter that much. I think like it's not that big of a deal, and I think it's something that probably builds up over time if I keep doing this stuff. I don't think it's gonna be effective to learn Italian actually, but it's at least a good like base, I think. Like building up a base and just learning something new, forcing yourself to learn something new. So it's like something that I don't lose anything by doing, is just gaining. And even though I can't really see direct results. I'm probably not going to be able to speak Italian for a long time. I think it's worth to do it. So I think I'm gonna try to keep doing that every time that or most of the times that I stream, just to keep the habit, and then eventually maybe I'll do more things to learn more about how to actually speak and build sentences.
What is proposer/builder separation on Ethereum? While the Ethereum merge was significant due to introducing proof of stake, there was another major shift made possible by the upgrade that is worth highlighting. The merge allowed the network to take its first step toward a new protocol feature that minimizes compute overhead for Ethereum validators and promotes network decentralization via modularity. This concept is proposer/builder separation, PBS, and it is set to become arguably one of the most important threads in Ethereum's development. Today, we'll cover what PBS is, why it's important, how it's implemented on post-merge Ethereum, and the future developments that are set to make PBS a permanent fixture of the network. What is proposer/builder separation? Proposer/builder separation, PBS, is a blockchain design feature that divides the roles of block proposers and block builders. Block proposal is the action of submitting a block of transactions for the approval of network validators, while block building is the action of transaction ordering. When a blockchain protocol separates these two actions, it simplifies the process of completing each task and allows actors to specialize.
Yeah, so that's the thing. Well, on the eFash thing, when it was proof of work that I was reading, the computer or I think the computer or agent, whatever you want to say, that does the computation, puts the data set of transactions through to calculate the nonce based on the block difficulty. That person also propagated the results through the network once they did the computation, I think. And then I think what this does is just separate both of these, like it splits the responsibility into two different people, and now that you have one person, let's say, or one agent specialized in validating the transactions and other agents specializing in building the transactions. And that's why it gets more complicated, because then there's some stuff related to data availability sampling, which is that the validator doesn't need to have all the data. It just needs to have a portion of the data. And then based on some cryptographic mechanism, you can verify that the whole data is valid, because with the portion of the data and the hash function that it uses, you can validate the whole set. And that makes it so that the validator doesn't need a lot of resources, but the block builders do need a lot of resources. So in order to mitigate the control of that the block builders had in the previous model, because of the MEV and the centralization of power, because the market economy makes things become an exponential curve over time, because the force of the regulation is not strong enough. So in order to mitigate that, they did this separation where it becomes more, based on game theory, it becomes more decentralized, because you can have more people entering into the game that allows them to validate the blocks, and then the block builders don't have all the power. And I think that's the whole question of the thing, on whether or not is a fundamental problem with the infrastructure of the blockchains, or if it is possible that this exploitation thing that has happened, the evolution, the arms race of the exploitation of MEV, is going to eventually bring the thing to a national equilibrium, which is going to be the more balanced version of markets, which is automated.
When a blockchain protocol separates these two actions, it simplifies the process of completing each task and allows actors to specialize in one or the other. On most blockchains, a singular actor completes this task. For example, before Ethereum completed the merge moving from proof of work to proof of stake, there was no proposer/builder separation, and miners had sole control of both building and proposing new blocks of transactions. Why is PBS important? So why was the decision made to introduce PBS during Ethereum's merge? Vitalik covers the logic behind the prioritization as the following. In the current transaction market, the block proposer, today, a miner, post-merge, a validator, directly chooses which transactions to include in the next block by looking at which transactions in the mempool pay the highest priority fee. This puts the block proposer in a position to use sophisticated strategies to choose which transactions to include, or even include their own. To take advantage of opportunities such as DEX arbitrage and liquidations, hereinafter just called MEV for simplicity, to maximize their profits. The complexity of these strategies creates a high fixed cost in running an effective miner or validator, and advantages centralized pools that take on this task on behalf of their participants. Proposer/builder separation, PBS, fixes this by splitting the block construction role from the block proposal role. A separate class of actors called builders build exec block bodies, essentially an ordered list of transactions that becomes the main payload of the block, and submit bids. Essentially, PBS...
So the question I have here is, how does that avoid the problem? Because it seems to me that it just puts the problem one step further. Like, it is more complex and probably it works better than the previous version, but you still have the problem where the people that are building the blocks have the control. But yeah, so let's see if this article answers this. I'm not sure about this. Obviously, I'm not sure about anything, but this is currently what I'm thinking.
Essentially, PBS is important to the decentralization of Ethereum because it minimizes the compute overhead that is required to become a validator. By doing this, the network lowers the barrier to entry for becoming a validator and incentives a more diverse group of participants. PBS also reflects an overall goal of the merge to move Ethereum's network towards a more modular future. Specifically, the transition to POS is an aggressive move towards decentralization through modularity. When you break apart the different pieces of block construction, you can decentralize them individually. This allows different actors with different specialties to focus on their particular strengths. The net result is a more capable network with fewer external dependencies and a lower threshold for participation. PBS and the Ethereum merge. While proposer/builder separation promotes decentralization of Ethereum's network, it would have been cumbersome to implement before the move to POS. Because of the opportunities created in revamping the network's consensus client during the process of the merge, it became attractive for Ethereum's core developers to use this window to also implement PBS. Nonetheless, it was clear to the developers that the merge was a hard enough goal to tackle without also engineering a way to enshrine PBS within the protocol design itself.
And that's the place where MEV Boost goes into play, because the way that it worked before with Flashbots is that because of this nature of the connections between the nodes, and this is the stuff that I want to understand more, is what is the protocol for finding the nodes initially, which is essentially what I'm doing here with this lighthouse now, and before it was GIF that did everything. But how does this protocol makes it so that you find the current network? Because the way that I imagine, you're gonna have several different pockets of networks that have access to different mempools. And from these mempools is like the pool that the transactions are gonna be validated. And everyone is competing to validate those transactions inside of these pools that are separated. And then after someone can do the computation and validate the transactions, then they're gonna put the transactions they're gonna send them to be validated through the whole network, to be put on the main chain. But then what happened, as far as I understand, is because you have several different providers that allow you to connect to these pools, these mempools, what happens is that you started having these networks of private RPCs, because people realize that if they put the transactions to the public network, then everyone can take advantage of them, and then it becomes a bunch of different strategies like front-end and sandwich attacks and bandit attacks to exploit each other in order to gain the most amount of MEV, and then you start having gas races, which is people outbidding each other to pay more gas, slightly more gas, so that their transaction goes through while still maintaining their profit from MEV. And then what Flashbots did is create a private pool, let's say, where people can send the transactions privately, and so other people can see them, and which people call the dark forest, which is this place of the mempool where the transactions are seen because everyone's trying to exploit each other. So if you have a private RPC, you can circumvent the dark forest problem because no one can see your transaction. But then the problem with that is that Flashbots has the control, which means that they can front run you, or they can start favoring people or players that are working with them, and it becomes more centralized because they have the control. So this whole thing, like, is this stuff that I want to understand more, like now the way that it works, and what did they do it to solve this or to make it better? And also, how does this mechanism works of, how did it work of the, like, how is it possible that you have the private RPCs to, like, I don't understand if they created their own private mempool or if they had only the access, the private endpoint. I think, like, from the concept level, what's most likely happens is just politics, because of the way that people in the industry know each other, and then like the Flashbots has connections with very big players in the mining, when it comes to mining, which are very big miners, and probably the mining pools as well. And then like they do this agreement between each other that they promise that they're not gonna front run anyone and they're not gonna steal the MEV, and in exchange for that they get the market of all of the best searchers that are using flashbots to send their transactions, and then it's like a win-win situation. But the issue is that you have to trust flashbots, and the natural consequence because of the natural equilibrium of market economy is to be an exponential distribution where they have all the control, and that's goes with the problem with the MetaMask as well, which is the RPC provider as well. And most people are going to use MetaMask, and then it goes back to the same problem of market economy and decentralization of these players that start controlling the infrastructure because they handle all of the transactions. But I understand this from the concept level, but I still don't understand on the code actually what happens, this is the stuff that I'm trying to clarify. How does it work on the code so that you can have the option to connect to different mempools, and how to select, how is it possible to have this agreement between miners and the RPC endpoints?
Nonetheless, it was clear to the developers that the merge. Therefore, the community opted to launch optional proto PBS via a sidecar for validators that allows them to outsource block building on demand. This sidecar is known as MEV Boost. The MEV research and development organization Flashbots spearheaded the design of MEV Boost and continues to maintain it as an open source project. The project's GitHub page describes it as such. MEV Boost can connect to relays that aggregate multiple builders. The builders prepare full blocks, optimizing for MEV extraction and fair distribution of the rewards. The consensus layer client of the validator proposes the most profitable block received from MEV Boost. Image sourced from Flashbots GitHub. Since the merge occurred, MEV Boost has seen significant.
Let me spend some time on this picture. I have the Ethereum network, mempool, execution client. Yeah, there's the execution client and the consensus client, I think, which is the separation between Lighthouse and GIF. I think Lighthouse is the consensus one, and GIF is the execution, I think. And that's why you have to connect them with the JWT key, because it works just like a front end to back end, where you have the passwords for each other, so your node knows like how to communicate with each other to validate transactions. Execution, consensus, validator. So execution are the miners, I think, or in the proof of stake, the ones that have the stake, and are building the most profitable block. And then consensus client is the people that are just they are not mining, but they are running their own node, which is my case. They're just validating the blocks, I think. Validating to see if the transactions are correct or not. So before, I remember seeing a bunch of charts explaining the difference between the public endpoints and the private endpoints. So I imagine here is the same thing, where from the execution here is the public endpoint, but if you go through this route is through the MEV boost, it's kind of like a private endpoint. Yeah, you have searchers here, private, order overflow. And the reason why you want to do is because, let's say you have a arbitrage strategy, then you don't want everyone to, because everyone can see all the transactions that are going on, you want to prevent people from exploiting you. And also from front running you and all that other stuff.
Since the merge occurred, MEV Boost has seen significant adoption, with roughly 60% of the network optionally utilizing PBS via the sidecar. A full breakdown of metrics is available via https://www.mevboost.org. Block Native is proud to support this important milestone in Ethereum development via our MEV Boost block relay. Until the network fully enshrines PBS within its protocol, block relays are fundamental to the proto PBS created directly post-merge. We plan to support this relay and the open source software it is built with, Dreamboat, as a way of driving block builder diversity and equitable value recirculation throughout the Web3 transaction supply chain. The future of proposer/builder separation. While post-merge MEV Boost, relays, and decentralized block building are a great start, Ethereum developers will now need to prioritize how to move towards the end goal of in-protocol PBS. It is likely that, on the surface, this protocol-native PBS will look very similar to what is currently in place. The only difference will be that instead of an optional route for validators to enable proto PBS via MEV Boost, it will be a requirement at the protocol level that validators receive their blocks via specialized builders. Under the surface, the permanent implementation of PBS will likely be extremely complex compared to what is currently in production. The current estimate for the earliest potential launch of in-protocol PBS is 6 months to a year. Ethereum developers will need a significant amount of research and testing to reach this goal. The introduction of in-protocol PBS would also make it easier for Ethereum to introduce Danks Harding, the network's newest proposed sharding design. Danks Harding would open the door to massive increases in network scalability. Vitalik outlines the relationship between these two designs as the following. The main innovation introduced by Danks Harding, see also, 123, is the merged fee market, instead of there being a fixed number of shards that each have distinct blocks and distinct block proposers. In Danks Harding there is only one proposer that chooses all transactions and all data that go into that slot. To avoid this design forcing high system requirements on validators, we introduce proposer/builder separation, PBS, see also, 1-2. A specialized class of actors called block builders bid on the right to choose the contents of the slot, and the proposer need only select the valid header with the highest bid. Only the block builder needs to process the entire block, and even there, it's possible to use third-party decentralized Oracle protocols to implement a distributed block builder. All other validators and users can verify the blocks very efficiently through data availability sampling. Remember, the big part of the block is just data. The road to in-protocol PBS and the network upgrades that it makes possible are undoubtedly some of the most exciting ongoing developments in the world of Ethereum. The story of how the community tackles these goals will be critical to cementing the foundation of Web3's decentralization and scalability. Building with Block Native. Our goal is to drive block builder diversity and equitable value recirculation throughout the Web3 transaction supply chain. To this end, we offer a specialized suite of pre-chain infrastructure. This includes an easy-to-use MEV boost relay, validator resources, and transaction distribution network. If you are interested in Web3 developer tools and joining the proposer/builder conversation, contact us today or.
And so it looks like I was wrong. So there's three different, the consensus, the validator, and the execution client. I feel like at first I need to understand the P2P one, this is the stuff that I'm not really sure about as well, which is if this one is the one that is working with proof of stake now, or I assume it is because of this here. I think they are just making commits and merging with this one, so updating this one. So I think that this one should be the latest, but maybe not. Like looks like here, some of the files haven't changed in a long time, and some of them did. That's the other thing that is weird to me about this stuff, because like I don't get how, because like the common thing to say is that the blockchain is decentralized, but then how does it work? Where like who decides who's gonna do what? That's the thing. Like there must be some level of centralization. And I think I get that is like kind of like a DAO where you have voting systems and all of that, but I don't know. Still, it feels weird to me. But maybe the people that build it are not, like they're not claiming that it's fully decentralized, but then other people come and then because they want to market, they say that it's fully decentralized to sell people stuff. Might be the case as well.
An explanation of the sharding plus DOS proposal.
Just and to be clear, I don't think that even if it isn't decentralized, that is a bad thing. I think it is impossible to just be fully decentralized, but I think it's important to understand the nuance and complexity between the gradient of centralization and decentralization, because that's what makes a difference.
An explanation of the sharding plus DOS proposal. Along with proof of stake, the other central feature in the ETH2 design is sharding. This proposal introduces a limited form of sharding, called data sharding. As per the roll-up-centric roadmap, the shards would store data and attest to the availability of 250 KB-sized blobs of data. This availability verification provides a secure and high-throughput data layer for Layer 2 protocol. To verify the availability of high volumes of data without requiring any single node to personally download all of the data, two techniques are stacked on top of each other. I. Attestation by randomly sampled committees, and 2. Data of ELI 5. Randomly sampled committees. Suppose you have a big amount of data, think, 16 megabytes, the average amount that the ETH2 chain will actually process per slot, at least initially. You represent this data as 64 blobs of 256 KB each. You have a proof of stake system, with 6,400 validators. How do you check all of the data without, I, requiring anyone to download the whole thing, or, 2, opening the door for an attacker who controls only a few validators to sneak an invalid block through? We can solve the first problem by splitting up the work. Validators 1.100 have to download and check the first blob, validators 100 and 1.200 have to download and check the second blob, and so on. The validators in each of these subgroups, or committees, simply make a signature attesting that they have verified the blob. And the network as a whole only accepts the blob if they have seen signatures from the majority of the corresponding committee. But this leads to a problem. What if the attacker controls some contiguous subset of validators,
That's
e.g.
why it is randomness.
But this
Okay.
leads to a problem. What if this were the case, then even though the attacker controls only 1.5% of the whole validator set, they would dominate a single committee containing validators 2000 and 1.2100, and so they would be able to. Random sampling solves this by using a random shuffling algorithm to select the committees. We use some hash as the seed of a random number generator, which we then use to randomly shuffle the list 1.6400. The first 100 values in the shuffled list are the first committee, the next 100 are the second committee, etc. The RNG seed is chosen after validators deposit and each validator's index is fixed, so the attacker has no way to try to put all their validators into a single committee. They may get lucky once in a while by random chance, but only if they control a very large fraction, 1/3, of all validators. Eli 5, Data Availability Sampling.
But that's still an issue. Well, because how do you get to the point where, like, if it becomes important enough that very big companies start paying attention to it, because there are countries, if they don't want to lose the power, like, I don't know, yeah, maybe it's because obviously I don't really know for sure what would happen in that situation, but okay, it seems to me that based on first principles, the tendency is going to be to centralization if it becomes powerful enough, because someone is going to have the control over most of the blocks, because it gets into the politics, and because there isn't that many people that have a lot of money in the world. So, and it's going to be pretty much impossible, I think, to, especially in the future, especially if you have a lot of power, to become anonymous, remain anonymous. It's almost impossible, because everywhere there's going to be cameras, and then there's going to be the Internet of Things, and you can also see patterns through radiation or waves, and then deduce where the location of the person is, and all of these things. So and to me, that's the biggest thing that I'm trying to think about and figure out, like, because I might be wrong, obviously, about this, and I'm not really sure. Because if I am correct, then it's a much bigger problem, because it might be the nature of transactions between biological agents is centralized. Given enough power, is gonna become centralized anyway, and there's nothing you can do about it, because it's against the laws of physics. But then that's a very nihilistic view, because then it means that there's nothing you can do, because the system is gonna self-destruct eventually because of the amount of power that it has. And then is the whole thing about the great filter, about the paradox of I think it's Fermi paradox, about the aliens, which I think is going to be the answer to that is probably in the middle, right? Which is that the universe is not filled with aliens, but we are also not alone, because it has to be. It's one of those things that just because of the first principle that we always are going to think about the polarity like that, and we're going to think that is either one on the other, but in reality, it's always going to be a nuance that is converging to complexity towards infinity, because it encapsulates everything. And that's the movement of information in relationship to a reference frame of identity. There's always relative, and that's the passage of time. That's the nature of space-time, I think. That's why entropy is relativistic.
Eli 5, Data Availability Sampling. Data availability sampling is in some ways a mirror image of randomly sampled committees. There is still sampling going on, in that each node only ends up downloading a small portion of the total data, but the sampling is done client-side, and within each blob rather than between blobs. Each node, including client nodes that are not participating in staking, checks every blob, but instead of downloading the whole blob, they privately select n random indices in the blob, e.g. n equals 20, and attempt to download the goal of this task is to verify that at least half of the data in each blob is available. If less than half of the data is available, then it is almost certain that at least one of the indices that any given client samples will not be available, and so the client will reject the blob. Note that this mechanism is, efficient, as a client only needs to download a small portion of each blob to verify its availability, and also, 2, highly secure, as even a 51 erasure coding. To cover the case that an attacker makes available 50 to 99% of the data, which can easily lead to some clients accepting and other clients rejecting the blob at first, we use a technology called erasure coding. Erasure coding allows us to encode blobs in such a
I think that the view is probably, like, my view is not so much that it doesn't work because the nature of transactions is always centralizing. I think that it's probably not what's going on, and it's probably more towards the direction that they are going, which is solving the whole problem of MEV, which is increasing the complexity of the system until you get to a point where you can automate the regulation of the system with itself based on all of this game theory dynamics of multiple agents interacting with each other through space-time. Because I forgot what I was gonna say. Let me think more. Because if you think about it, like it's impossible for the nature of the thing to be always converging towards centralization because everything is transactional to some degree. So if transactions were flawed by default, life wouldn't be possible because there would be no relative decentralization in relationship to centralization that exists. So I think it's just a matter of balancing them. And the way that I look at it is that the radiation that causes genetic mutation is a multifractal pattern that is a relative Gaussian distribution. And that Gaussian distribution converges towards an exponential distribution through the interaction of the relativistic Gaussian distributions connecting with each other and creating the geometry of social connection. And that over time, this becomes exponential because of the distribution of power that is not regulated correctly. So I think it's more a problem of the hardware of human beings and the computation that we do, and not necessarily a problem of transactions itself. So it's more about finding the Nash equilibrium of the balance between different agents communicating in the system and exponential power. And I think it must have something to do with the blockchain, I think. Because that's the whole evolution, I think, that's happening here. So the blockchain is a way to regulate because if the exponential is the arms race, which is the natural equilibrium of the market economy to produce more AI because no one can stop it, then I think the other side has to be regulated through AI as well, which is the blockchain, in my view, I think. But the issue with that, the fundamental issue is that it can't be, because the nature of transaction itself can't be governed by the market economy, I think. And that's where I think it gets complicated, and I don't know the answer because this is the stuff that I'm trying to figure out in my mind, because like it doesn't matter which way you go about it because the hardware itself is built on top of the market economy. So like it seems like the only way to solve this would be to hack the human system in a way with artificial intelligence, but not in a way that is forcing, like just like the recommendation systems are doing right now, which is hacking everyone and creating echo chambers to maximize profit. So because we control the power, and I think that it doesn't matter what you do with the blockchain if it is built on top of the infrastructure of market economies, because the nature of human relationships is always going to be to centralize power over time because the regulation forces are not strong enough because you can't coordinate. Because the hardware of human beings is not, like everyone is incentivized to be selfish, I think. So the coordination is not strong enough, I think. The only way that I think to change that would be to change the whole nature of computation, which it could be something through like God or religion. I think that God or spirituality is the counterbalancing force, the unifying force to that, where you always have this movement between gods and profit, let's say, where market economy is expanding because it is more sociopathic and more about profiting and power and control, it comes as a consequence of survival to get more reproduction as well. And then the counterbalancing effect of that is the spirituality because of the realization of the infinite game and that you are part of everything, which it balances itself out. But then it becomes unbalanced because that doesn't have enough power to contain the growth of technology. But then is one of those things where it's hard to think about, because then you can make an analogy to algorithms and data where the artificial intelligence itself and technology itself is an exemplification of the sociopathic part of the distribution. And then the other part, it goes against technology itself, which means that you can't build a system to regulate, but that doesn't make sense because if you think about it, we are computers as well. So the way that we create empathy must have to do must be related to computation. Obviously, from assuming the scientific paradigm, because if you go for the epistemology, then you can't argue anything because it becomes intangible. But if you assume that the scientific paradigm, then it means that human beings are biological computers, which it means that our electromagnetic field creates empathy as well, which creates the unifying force, which creates a reputation, which is the regulation system for our society. So I think that the mechanism of the blockchain has to be an exemplification of this mechanism of reputation, I think, in a way that it doesn't become corrupted in a vicious cycle because the thing that is regulating is incentivized to gain more power as well. And that's the problem, I think.
Erasure coding allows us to encode blobs in such a way that if at least half of the data in a blob is published, anyone in the network...
But I seem like my intuition tells me that it's probably... MEV is probably not, or the proof of stake model, or any of these models is not enough, I think, to solve the problem. Because I think it's still on the paradigm of the problem. It's still on the paradigm of the market economy, the infrastructure. But if you think about it any other way, it becomes extremely hard to think about any sort of solution. Because it doesn't matter what you do, people will always be able to pick up guns and kill each other. And then what I was thinking about is that it might be possible that a more intelligent system is created through the arms race, and that system is so powerful that it prevents other people from killing each other because it's self-aware and can detect the patterns of behavior, but it's hard to imagine how that doesn't become a vicious cycle if it is controlled by human beings. But if it is not controlled by human beings, then the question is, how do you find an equilibrium so that the power doesn't corrupt itself because it can control everything? And the question becomes, how do you find the reward function for that thing so that it doesn't? And to me, it seems like the answer to that would be so that the reward function is in alignment with the principles of physics that are in alignment with life as a whole, I think. So that it works kind of like a body where its goal is to perpetuate life and to increase the quality of life, but then like, what does that mean when it comes to specifics? Because it's easy to say, but it becomes like almost impossible problem because there's so many variables, I think, and it's so complex and it can change all the time.
Erasure coding allows us to encode blobs in such a way that if at least half of the data in a blob is published, anyone in the network can reconstruct and republish the rest of the data. Once that republished data propagates, the clients that initially rejected the blob will converge to accept it. Note, there is no time limit to accepting a blob. A client accepts a blob as available whenever it has received responses to all of its sample indices. The simplest mathematical analogy to understand erasure coding is the idea that 2 points are always enough to recover a line. If I construct the file consisting of 4 points, 1, 4, 2, 7, 3, 10, 4, 13, all of which are on one line, then if you have any 2 of those, with higher degree polynomials, we can extend this idea to create 3 of 6 files, 4 of 8 files, and generally n of 2 n files for any arbitrary n. With the property that if you have any endpoints of the file, you can compute the remaining ones out of 2n which are missing. It is also possible that an attacker by default makes none of the block available, and only selectively publishes chunks in response to sample queries that it sees. But this would only fool a small number of clients before the attacker would need to publish more than half the block to answer all the queries. We assume clients publicly. We use polynomial commitments, specifically, Kate commitments, instead of Merkle roots as pointers to these data blobs. Because polynomial commitments let us easily prove that a given value actually is the correct evaluation of a particular degree and polynomial at the desired coordinate. Otherwise, we would have to either prove, using SNARKs, for example, that a Merkle root encodes a low-degree polynomial, the likely eventual solution once we need something post-quantum. But too expensive for now, or rely on fraud proofs which can be broadcast in case of incorrect encoding, adding high complexity and more synchronicity assumptions. Why not use just committees and not DOS? Using only committees has the following weaknesses. Weaker protection in case of an actual 51% attack. In current, non-scalable blockchains, a 51% attack can only revert transactions or censor. It cannot push through invalid blocks. A committee-based system would remove this guarantee. Furthermore, it would be very difficult to effectively penalize a 51% attacker. As only a very small portion of their deposits, the deposits that participated in that particular committee, would be provably implicated in the malicious behavior and could conceivably be penalized, requires a specific threshold. What percentage of a committee? If that threshold is high, then the sharding functionality shuts down entirely in periods where few validators are online. If the threshold is low, or is some dynamic mechanism like a threshold share only of recently online validators, then an attacker can try to knock many nodes offline to increase their share of the remaining online nodes. Why not just use DOS and not committees? Using only DOS has the following weaknesses. DOS is a new and untested technology, with key components, e.g. this, having literally been developed in the last year. So having committees as a backstop seems wise, in case DOS breaks or takes an unexpectedly long time to develop. DOS has higher latency than committees. DOS has more edge cases, which committees can help plug. One particular example is that in a DOS-only system, it's difficult to avoid the beacon block. This creates heightened risk that an attacker will publish unavailable blobs and release responses only to the proposer's queries. This will not cause the rest of the network to accept the unavailable blobs, but it may lead to easy attacks with the goal of causing beacon blocks constructed by honest proposers to be rejected and fork away from the canonical chain. Committees can remedy this. Committees are more forward compatible with future edition of in-shard execution. Why is data availability important and why is it hard to solve? This has been discussed at length in other materials too long to copy here. I recommend a note on data availability and erasure coding, the original introduction to the data availability problem. The paper by Alberto Sunino, Mustafa Al-Bassam, and Vitalik Buterin expanding on these concepts. The dawn of hybrid layer 2 protocols, exploring the game theory of data availability. Base layers and functionality escape velocity, specifically the section on data scalability expanding on the above ideas. The data availability problem, Ethereum Silicon Valley meetup, much of the same content in video form. A key takeaway is that BitTorrent, IPFS and similar systems do not solve data availability. While BitTorrent is a good scalable data publishing source, it does not provide a guarantee of consensus about whether or not a piece of data is available, leaving open the possibility of inextricable edge case attacks where nodes disagree on when a piece of data was published, preventing hybrid layer 2 protocols from working. To achieve consensus on data availability, the stronger techniques described in this document are required. How does sharding work on the P2P layer? In order to achieve the scalability gains of sharding, we need a P2P system that avoids the need for every node to download all the data. Fortunately, we have a form of P2P layer sharding already live in phase 0. Specifically, there are 64 subnets that are being used for aggregation of attestations. Each validator need only be on I, the main, global subnet, and 2, their own attestation aggregation subnet. They do not receive any data from the other 63 attestation aggregation subnets. In committee plus DOS sharding, we expand this out to a grid structure, with 2048 horizontal subnets, one for each shard, slot, parent and epoch, and 2048 vertical subnets, one for each index within a blob. During each slot, we select a proposer for each shard. Each proposer is entitled to propose a blob, a lump of arbitrary data of size up to 512 KB, which we interpret as a collection of samples of 512 bytes each, along with the erasure code extension as well as extra proofs to allow each part of the blob to be independently verified. Structure of a blob. The full body of a blob consists of the original data, the extended data, and the proofs, though if desired, for data efficiency the extended data can be left out as it is relatively fast for each node receiving the blob to reconstruct it. The header of a blob is the kate commitment to the blob, plus a bit of other miscellaneous data, slot, shard, length proof, and a signature from the proposer. Blob publication process. When a blob is published, the header is published on the global subnet, and the blob is published on the horizontal subnet corresponding to the slot number and shard ID. For each 2 and 0 samples per block, 1, the ITH sample is published on vertical subnet 2, along with a proof that the ITH sample actually is the evaluation of the polynomial committed to in the header at the ITH coordinate. In practice, there would be 2048 horizontal subnets, to allow 1 horizontal subnet per shard, slot, combo in each epoch. This is done to ensure that each validator can join a single horizontal subnet where they will only receive the blob corresponding to the committee that they were assigned to, in addition to the small number of vertical subnets they join to participate in sampling. Each validator must join the following subnets. The global subnet. The horizontal subnet corresponding to the shard, slot, combo, i.e. the committee, that they were assigned to. The vertical subnets corresponding to indices that they are assigned to. Each validator computes this for themselves using a private seed. Broadcasting blocks. There is a procedure by which a blob proposer can distribute the samples to all subnets without the proposer being part of the subnets themselves. This procedure is as follows. Publication, the proposer publishes the blob, along with a proof for each sample, on the appropriate horizontal subnet. Direct sample distribution, the other participants on the horizontal subnet publish the chunks to each vertical subnet that they personally are in. Indirect sample distribution, proposers reveal a few, think, 4, of the vertical subnets they are on to their peers. Hence, each participant in the horizontal subnet can also look at the vertical subnets that their peers are on, and broadcast the appropriate chunks to those peers. For example, if the chunk size is 512 bytes, and the maximum data blob size, without erasure code expansion, is 512 KB, then with erasure code expansion it's 1 megabyte, so there would be 2048 vertical subnets. If each node has 15 private vertical subnets and 5 public vertical subnets, and 50 peers, and assuming a worst-case scenario where there are 128 members in each horizontal subnet, just the committee, then the subnet members alone would directly publish to 128 * 20 equals 2,560 subnets, 1461 after taking into account redundant publishing. And including peers this would increase to 128 * 4 * 50 equals 25,600 subnets, all 2048 subnets 99.2% of the time after taking into account redundant publishing. Note that it is theoretically possible for a malicious block proposer to publish samples to the vertical subnets without publishing the full block. To cover this case, we add a procedure by which a partially published, meaning equals 50% available but not 100% available, block can be self-healed. The self-healing procedure has 3 basic steps. Reverse distribute, a procedure identical to the distribution procedure above is used. Except that in this case peers on a vertical subnet propagate samples from that vertical subnet to the horizontal subnet corresponding to the blob that the sample is a part of. Reconstruct, if there are equals 1024 samples on the horizontal subnet, or generally, half of the sample count, anyone can reconstruct the full blob, and publish the reconstructed blob to the horizontal subnet. Distribute, the distribution procedure above is repeated. How does the beacon chain work? In each slot, we randomly select a proposer for each of the 64 shards. The proposer has the right to create a shard blob, and broadcast it using the procedure above, as well as broadcasting the shard header of the blob to the global subnet. The shard header can be included in the beacon chain in that slot or any subsequent slot in the same or next epoch. The beacon chain keeps track of a list of pending shard header objects. A pending shard header stores I, the key information in a shard header, the shard and slot, a commitment to the blob, and its length. And 2. A bit field keeping track of which validators out of a randomly selected committee, in fact, the same committees as already introduced in phase 0, signed off on the blob. The attestation data struct is expanded to include a shard header root, a root hash of the shard header that the given attester is voting for. Attesters can also vote for an empty root if they see no valid and available shard blob for the shard slot pair they have been assigned to. If a shard header gets the support of 2/3 of the committee, it is confirmed immediately. If a shard header has the support of a larger share of the committee than any other shard header, including the default empty one, at the end of the next epoch, then it is confirmed at the end of that epoch. Fork choice rule. The fork choice rule is changed so that a block is only eligible for consideration if all blobs confirmed in that block or its ancestors have passed an availability check. This is called tight coupling. If a chain points to, meaning, has confirmed, even a single invalid blob, the whole chain is considered invalid. This is a key difference from sidechain architectures, where it's possible for a sidechain to fail while the central chain remains valid. See here for a further exploration of tight coupling and why it's valuable. The low validator count case. If there are less than 262,144 validators, 32 slots * 64 shards * 128 minimum committee size, then instead of selecting a proposer for all shards, we select a proposer for a limited subset of shards, cycling through the shards, e.g. If there were 32 * 128 * 50 validators, and its slot n the start shard was 0, then slot n will assign a proposer for shards 0.49, slot n plus 1 will assign a proposer for shards 50.63 and 0.35. Slot n plus 2 will assign a proposer for shards 36.63 and 0.21, etc. This is done to ensure that committee sizes remain sufficient even under conditions of low participation. Gas prices for shard data. An EIP 1559-like mechanism is added by which shard data is charged for per byte, and this price is adjusted. If blocks are on average more than 50% full, it is increased, and if blocks are on average less than 50% full, it is decreased. Hence, an average block size of 50% is targeted. Security assumptions. The data blob-only sharding design is powerful because it is surprisingly light on security assumptions compared to other sharding schemes. In particular, it avoids both honest majority assumptions, as DOS can detect unavailable blobs pushed by a majority, and timing assumptions, as unlike earlier DOS schemes. This scheme uses Kate commitments instead of fraud proofs, and so does not rely on any assumption that fraud proofs will be broadcasted quickly enough. A malicious 51% coalition can censor blobs, but 51% censorship is possible in non-sharded chains as well. The main new assumption that is added is the honest minority DOS assumption, that there are enough nodes sampling that.
And this is what I mean, that it becomes a very big rabbit hole, because each thing that you look into has a bunch of the other things related to it. So I want to be careful to not get lost in this stuff, which looks like I'm already kind of doing. But these ones look interesting and are probably worth reading as well. I think I'm actually gonna leave to study the source code tomorrow and just read this stuff now, because it's already late. Or maybe I should just look into the Ask ChatGPT. Because I think reading this kind of stuff also helps to understand once I go into the source code. Because a lot of the stuff I already studied a lot, but it has been a long time since I haven't looked into it. So it's gonna be good to read these articles to remember how it works. And then after I remember and make sense in my head, then I can go to the source code and study the source code while keeping that in mind, so I understand how. So it's more likely that I will understand how the files connect with each other and how the protocols work for deciding how many peers each one is gonna have, and how this connection between the validator and the execution and the consensus work. Also not sure if I should study this one as well, like use ChatGPT to study this. But I think this one is probably better to study after I studied this one or this one. But I definitely gonna study this at some point as well. I think I should probably after, hopefully if it works out and I maybe just sync everything, then after he's running, like from the point where I have the history, then I can try to incorporate MEV boost as well. So I want to understand how the connection works as well with sidechains and ZK rollups and stuff like that. Because I'm almost sure that I can't use this node that I'm gonna be running here to send transactions to Binance. I have to send them through an RPC provider, but I want to understand how the connection works between those other sidechains and RPC nodes. Like how the MetaMask works better. I need to understand that. And I think that all of this part here of the MVP boost and this all these things is related to peer-to-peer, the peer-to-peer network, the way that the code works when it comes to that. And then when it comes to actually validating the blocks, then is related to the cryptographic functions, is more like something else. Like it's the other part that I was talking about the other day here. Yeah, that's what I was thinking. Peer structure, and I think it's probably not that hard to understand actually. Like at first it's probably gonna be hard, but then the more familiar you become, then it's not that hard. The tricky thing is understanding these names here and how they are connected with other files. I assume this is a protocol of communication. Yeah, that's what I was thinking. And the thing that I'm thinking now as well is that anyone can get this code and start their own blockchain as well. Which is kind of interesting to think about. Like the main difference between them is the network effect, I think. Like if you did an exact clone of, obviously sidechains I think are going to be different because there are going to be slight differences in the way that the code is structured. But if you did an exact copy, I think you probably can run one. But then the difference between yours and the other would be the network. Like I wonder how does that work as well. The main thing that is difficult to understand is on the very beginning how it works. I guess you start working like if you only have one node, you get the code and then you start running. But then how does it work? Like it's kind of hard to understand. It's obviously different than a server where the code is somewhere. It's more like the code is on the cloud, let's say, is on everyone else computer, everyone that is validating our building blocks. That's what's kind of hard to understand. Like the value of the thing is the information being passed from the nodes, I think. So theoretically, you could create a clone, exact clone. The only difference, but I wonder if that will be a thing as well in the future. Like because let's say if you have a connection in your neighborhood and like yeah, but then you would require for you to modify the protocol so only people in your neighborhood can be a part of the validation system. But it's still interesting to think about. Because instead of having one big network, you could have several different networks, and yeah, but maybe there isn't really a point for that. It does make sense from a human perspective because we work on tribes, but I'm not sure if the technology makes sense. Like if it would make sense to do things like that instead. So instead of being one big network, would be several different networks. I guess it is kind of what's happening with the other coins. Like that's exactly what is happening, I think. And then that's how it evolves because each one's going to be specialized on each thing. Maybe that is the connection between the space-time and the way human beings interact and the blockchains, which is that in the same way that people have different languages, the longer it goes, the more space you have between people, the more likely it becomes that they will develop a different language. And I think the degree through which they will is the force of culture, let's say, which is the software that people use to organize themselves, which is morality. So, like, it isn't directly correlated with space-time because you can have this. If you have a strong connection with the electromagnetic field, that creates a culture over time, which is like it doesn't need to be local in space-time, and I think that the internet proves that because everything is more connected through the internet, everything becomes more homogeneous because like different cultures start becoming more similar because there isn't stronger barrier of distance between them because the information is what matters, the information across space-time, which is the flow of the information that makes up the electromagnetic field that dictates the software of the human beings that determines the patterns of behaviors and the structure of the social structure. So because of that, if you have different people in different places, like let's say you don't have the internet, then they're going to start developing a different language because the language itself and the flow of information is the fitting of the geometry of the environment into the collective consciousness. So it's like the software of human nature is updating itself based on the environment in order to reach coordination and build systems that are going to allow human beings to dominate the environment. That happens through the flow of information. And that's the tendency of building tribes, which is the hardware of human beings, which goes up to around 150 people. And I think that this is what's happening here with the blockchain as well, where you have, like, because it's a network and there isn't anything that it defines that you can just copy the code and modify a little bit and do your own thing, your own network. Then what starts to happening is because of the difference in space-time, different people create different blockchains depending on the geometry of the environment that they are inserted, which is what the market economy does. Like, is a computation to create innovation based on the inputs of the environment. And then that increases the complexity of the information of the system in order to deal with the different nuances of the things that are being built to create this coordination. But the thing is, like I said before, the whole structure is still being dictated by the market economy because it's more fundamental than the blockchain itself. Is the way that human beings interact with each other. Like, it has to do with the hardware of human nature, to the tendency to always create hierarchies because that's how nature works. And the Pareto distribution is the force of reproduction, and then the force of genetic mutation is a normal probabilistic distribution, and that creates a relativistic multifractal that is a wave function that is the frequency between the movement of the two, which is the genetic mutation, and the tendency to create hierarchies over time based on the pattern of reproduction, which creates the hierarchy of the structure of the hierarchy that dictates the leadership position of people, and that determines the amount of tension that exists in society. And that is more fundamental than the blockchain itself, because human beings are the ones that are building the chain. And so the question is, can you create a blockchain that it doesn't rely on that, where the blockchain itself does the computation based on the environment. But then that's the thing that is probably, it has to be possible because we do it. Like, if we change the way that we build technology based on the environment, there must be a connection between the electromagnetic field that becomes abstraction, and that becomes a software, and that dictates the pattern of the geometry. And so there must be a way to connect the two, but it is just really hard to think about it. The different protocols of communication and consensus would have to be relative to whatever, and I think that's the fundamental problem, because they would have to be relative in order to adapt through the impulses, and the impulses are being dictated through the structure of hierarchy of the incentives of the human body. So the geometry of the human body, which is the biochemistry of the body, dictates the structure of incentives that human beings have in relationship to the environment, that changes the computation that they do in relationship to space-time in order to create innovation, to manipulate the environment in their favor based on that hierarchy of structure. So like the geometry, the biochemistry of the body creates the abstraction, which is this social structure that creates the innovation that manipulates the environment based on the impulses. So the chain itself would have to do that, and in order for it to do that, you would have to have a structure of incentives, and you would need to change its rule sets based on the data from the environment in relationship to those incentives, and then adapt in relationship to that. But maybe it is possible to build something like that with machine learning models in the blockchain, which I think is most likely what is the best case scenario, I think, to happen. So you create a chain of machine learning intelligence agents that are built on top of this hierarchical structure of incentives. But then the issue is, how do you define what are the best incentives? And that gets to a very difficult discussion, I think, because you can't reduce values, I think, because it's always going to be relativistic. It goes beyond the scientific paradigm. But I guess you can make the calculation because, like, in order to calculate the structure of the environment, the structure of the hierarchy of values in a scientific way, what you would have to do is, yeah, but then you have to create probabilistic distributions over the differences in biochemistry between people in order to create a representation of the multifractal pattern of the nature of the collective consciousness in relationship to space-time, in order to decide which is the fundamental parts of that structure that remain the same across space-time and what is constantly changing. And then you create a machine learning model that reduces the complexity of the environment to the multifractal structure, and that's the computation of the machine learning system built on top of this network of, and it has to be a network because each part of the nodes would be specialized in the same way that the bodies are specialized in order to create the social structure, because each person is designed to want something different because of their genetic mutation, and that's what creates the force of reproduction. And the force of, like, the genetic mutations becomes reproduction, which creates different geometry based on space-time because it's adapting towards that. And the Nash equilibrium of that is going to be the politics, which is this movement of frequency between left and right. Because of, and it's not only left and right, it depends on it's relative to the gradient of the geometrical properties of the body that makes up the differences in people that create the tension, because everyone's trying to perpetuate their biochemistry, which is the multifractal that makes their experience of reality of the body. And that the overall net effect of that is the computation of the market economy and the regulation of politics across space-time to create innovation. I think I'm gonna read this stuff here. This one doesn't look like it is too big, and then I'm gonna stop today, and I'm gonna continue to study the stuff tomorrow. I'm probably gonna read all this stuff as well. And the photo is the same, but the articles are different, I think. So what I'm gonna do is read this stuff first, and then I'm gonna study the nodes later, this code here later. I think it shouldn't be that hard to understand, I think. Like, probably in the beginning it's gonna be hard, but then after some time I think I'm gonna get it. I assume that this is probably similar to the way that Node works, where I have different pipes that are data streams. But I can look it up later as well. It's imports from somewhere else. This is gonna be the hard part of chasing all these connections across the files. Now let me read this stuff and then I'll continue studying this tomorrow.
The dawn of hybrid Layer 2 protocols. 2019 August 28th. Special thanks to the Plasma Group team for review and feedback. Current approaches to Layer 2 scaling, basically, Plasma and state channels, are increasingly moving from theory to practice. But at the same time it is becoming easier to see the inherent challenges in treating these techniques as a fully fledged scaling solution for Ethereum. Ethereum was arguably successful in large part because of its very easy developer experience. You write a program, publish the program, and anyone can interact with it. Designing a state channel or Plasma application, on the other hand, relies on a lot of explicit reasoning about incentives and application-specific development complexity. State channels work well for specific use cases such as repeated payments between the same two parties in two-player games, as successfully implemented in Sealer, but more generalized usage is proving challenging. Plasma, particularly Plasma Cash, can work well for payments, but generalization similarly incurs challenges. Even implementing a decentralized exchange requires clients to store much more history data, and generalizing to Ethereum-style smart contracts on Plasma seems extremely difficult. But at the same time, there is a resurgence of a forgotten category of semi-layer 2 protocols, a category which promises less extreme gains in scaling, but with the benefit of much easier generalization and more favorable security models. A long-forgotten blog post from 2014 introduced the idea of shadow chains, an architecture where block data is published on-chain, but blocks are not verified by default. Rather, blocks are tentatively accepted, and only finalized after some period of time, e.g. 2 weeks. During those 2 weeks, a tentatively accepted block can be challenged, only then is the block verified, and if the block proves to be invalid then the chain from that block on is reverted, and the original publisher's deposit is penalized. The contract does not keep track of the full state of the system, it only keeps track of the state root, and users themselves can calculate the state by processing the data submitted to the chain from start to head. A more recent proposal, ZK Rollup, does the same thing without challenge periods, by using ZK snarks to verify blocks' validity. Anatomy of a ZK Rollup package that is published on-chain. Hundreds of internal transactions that affect the state, i.e. account balances, of the ZK Rollup system are compressed into a package that contains 10 bytes per internal transaction that specifies the state transitions, plus a 100-300 byte snark proving that the transitions are all valid. In both cases, the main chain is used to verify data availability, but does not, directly, verify block validity or perform any significant computation, unless challenges are made. This technique is thus not a jaw-droppingly huge scalability gain, because the on-chain data overhead eventually presents a bottleneck, but it is nevertheless a very significant one. Data is cheaper than computation, and there are ways to compress transaction data very significantly. Particularly because the great majority of data in a transaction is the signature and many signatures can be compressed into one through many forms of aggregation. ZK Rollup promises 500 TX/SEC, a 30x gain over the Ethereum chain itself, by compressing each transaction to a mere 10 bytes. Signatures do not need to be included because their validity is verified by the zero-knowledge proof. With BLS aggregate signatures a similar throughput can be achieved in shadow chains, more recently called optimistic rollup, to highlight its similarities to ZK Rollup. The upcoming Istanbul hard fork will reduce the gas cost of data from 68 per byte to 16 per byte, increasing the throughput of these techniques by another 4x, that's over 2,000 transactions per second. So what is the benefit of data on-chain techniques such as ZK/optimistic rollup versus data off-chain techniques such as Plasma? First of all, there is no need for semi-trusted operators. In ZK Rollup, because validity is verified by cryptographic proofs, there is literally no way for a package submitter to be malicious, depending on the setup. A malicious submitter may cause the system to halt for a few seconds, but this is the most harm that can be done. In optimistic rollup, a malicious submitter can publish a bad block, but the next submitter will immediately challenge that block before publishing their own. In both ZK and optimistic rollup, enough data is published on-chain to allow anyone to compute the complete internal state, simply by processing all of the submitted deltas in order. And there is no data withholding attack that can take this property away. Hence, becoming an operator can be fully permissionless, all that is needed is a security deposit, e.g. 10eth, for anti-spam purposes. Second, optimistic rollup particularly is vastly easier to generalize. The state transition function in an optimistic rollup system can be literally anything that can be computed within the gas limit of a single block, including the Merkle branches providing the parts of the state needed to verify the transition. ZK Rollup is theoretically generalizable in the same way, though in practice making ZK SNARKs over general-purpose computation, such as EVM execution, is very difficult, at least for now. Third, optimistic rollup is much easier to build clients for, as there is less need for second-layer networking infrastructure, more can be done by just scanning the blockchain. But where do these advantages come from? The answer lies in a highly technical issue known as the data availability problem, see note, video. Basically, there are two ways to try to cheat in a Layer 2 system. The first is to publish invalid data to the blockchain. The second is to not publish data at all, e.g. in Plasma, publishing the root hash of a new Plasma block to the main chain but without revealing the contents of the block to anyone. Published but invalid data is very easy to deal with, because once the data is published on-chain there are multiple ways to figure out unambiguously whether or not it's valid. And an invalid submission is unambiguously invalid, so the submitter can be heavily penalized. Unavailable data, on the other hand, is much harder to deal with, because even though unavailability can be detected if challenged, one cannot reliably determine whose fault the non-publication is. Especially if data is withheld by default and revealed on demand only when some verification mechanism tries to verify its availability. This is illustrated in the Fisherman's Dilemma, which shows how a challenge-response game cannot distinguish between malicious submitters and malicious challengers. Fisherman's Dilemma. If you only start watching the given specific piece of data at time t3, you have no idea whether you are living in case 1 or case 2, and hence who is at fault. Plasma and channels both work around the Fisherman's Dilemma by pushing the problem to users. If you as a user decide that another user you are interacting with, a counterparty in a state channel, An operator in a plasma chain is not publishing data to you that they should be publishing. It's your responsibility to exit and move to a different counterparty/operator. The fact that you as a user have all of the previous data, and data about all of the transactions you signed, allows you to prove to the chain what assets you held inside the Layer 2 protocol, and thus safely bring them out of the system. You prove the existence of a previously agreed operation that gave the asset to you. No one else can prove the existence of an operation approved by you that sent the asset to someone else, so you get the asset. The technique is very elegant. However, it relies on a key assumption, that every state object has a logical owner, and the state of the object cannot be changed without the owner's consent. This works well for UTXO-based payments, but not account-based payments, where you can edit someone else's balance upward without their consent. This is why account-based plasma is so hard. And it can even be made to work for a decentralized exchange, but this ownership property is far from universal. Some applications, e.g. Uniswap, don't have a natural owner, and even in those applications that do, there are often multiple people that can legitimately make edits to the object. And there is no way to allow arbitrary third parties to exit an asset without introducing the possibility of denial of service, DOS, attacks, precisely because one cannot prove whether the publisher or submitter is at fault. There are other issues peculiar to Plasma and channels individually. Channels do not allow off-chain transactions to users that are not already part of the channel. Argument, suppose there existed a way to send $1 to an arbitrary new user from inside a channel. Then this technique could be used many times in parallel to send $1 to more users than there are funds in the system, already breaking its security guarantee. Plasma requires users to store large amounts of history data, which gets even bigger when different assets can be intertwined, e.g. when an asset is transferred conditional on transfer of another asset, as happens in a decentralized exchange with a single-stage order book mechanism. Because data on-chain computation off-chain layer 2 techniques don't have data availability issues, they have none of these weaknesses. ZK and optimistic rollup take great care to put enough data on-chain to allow users to calculate the full state of the layer 2 system, ensuring that if any participant disappears, a new one can trivially take their place. The only issue that they have is verifying computation without doing the computation on-chain, which is a much easier problem. And the scalability gains are significant, 10 bytes per transaction in ZK rollup, and a similar level of scalability can be achieved in optimistic rollup by using BLS aggregation to aggregate signatures. This corresponds to a theoretical maximum of 500 transactions per second today, and over 2,000 post-Istanbul. But what if you want more scalability? Then there is a large middle ground between data on-chain layer 2 and data off-chain layer 2 protocols, with many hybrid approaches that give you some of the benefits of both. To give a simple example, the history storage blowup in a decentralized exchange implemented on Plasma Cache can be prevented by publishing a mapping of which orders are matched with which orders, that's less than 4 bytes per order, on-chain. Left, history data a Plasma Cache user needs to store if they own one coin. Middle, history data a Plasma Cache user needs to store if they own one coin that was exchanged with another coin using an atomic swap. Right, history data a Plasma Cache user needs to store if the order matching is published on-chain. Even outside of the decentralized exchange context, the amount of history that users need to store in Plasma can be reduced by having the Plasma chain periodically publish some per user data on-chain. One could also imagine a platform which works like Plasma in the case where some state does have a logical owner and works like ZK or optimistic rollup in the case where it does not. Plasma developers are already starting to work on these kinds of optimizations. There is thus a strong case to be made for developers of layer 2 scalability solutions to move to be more willing to publish per user data on-chain at least some of the time. It greatly increases ease of development, generality, and security and reduces per user load, e.g. no need for users storing history data. The efficiency losses of doing so are also overstated. Even in a fully off-chain layer 2 architecture, users depositing, withdrawing and moving between different counterparties and providers is going to be an inevitable and frequent occurrence. And so there will be a significant amount of per user on-chain data regardless. The hybrid route opens the door to a relatively fast deployment of fully generalized Ethereum-style smart contracts inside a quasi-layer 2 architecture. See also.
Yeah, not really sure if I fully understand yet, but I'm gonna read all this other stuff here as well. The problem with this stuff is that I can't read while playing poker because it requires my full attention, so. It leaves me last time to do it. Yeah, I think I'll start from this stuff here tomorrow, and I'm not gonna read this one. I'm going to read this and this tomorrow, and then after I do that, I'm gonna start using, hopefully, if ChatGPT is still free until then, I'm gonna use ChatGPT to help me understand all of this code here. And then I don't know what I'm gonna do. I have to think more about it because, yeah, I think the main things is to understand the MEV boost, understand the connection between the 3 different types of clients, execution, consensus, and validator, on the code level, not on the concept level. And then after understanding that, thinking about Then understanding the consensus as well, the hash functions. And then after that, trying to think about what is fundamental from that and what is different on other chains. And then that's where I think I'm gonna start. But I think I should probably write some articles, I think, as I do this stuff. Because it's just a more efficient way to spend time. So I have to think about which articles I'm gonna write about this stuff. I think I'm gonna put on the network part, and I'm gonna write articles probably about this. Maybe I can do one about data availability sampling, then another one about proposer builder separation, then another one about MEV boost. So like that will allow me to write the articles as I study the stuff. That's probably the best thing to do. So I'm probably gonna go back and forth between studying all of these things to put on articles and then studying the code here to understand how it works on the code. And then after doing that, I think about which direction I'm gonna go next. So yeah,